Dear friends, we will discuss earthing system design for today's lecture. So, why earthing is important in HV substations, EHV substations, GIS substations? So, all these substations require earthing. Why it is required? What is the purpose of the earthing? And where it is required. So we will discuss earthing system design in details, some practical views. Practically, you can get more knowledge. Kindly go through complete lecture. Here we are going to discuss practical aspects also. So kindly go through complete lecture. We are going to discuss practical aspects. Very important topic. So, what are the contents or what topics we will discuss? Substation earthing, general overview. So, in general overview, why earthing is required? What is the purpose of the earthing, and why it is necessary? So, this overview will be discussed. Dangerous potential. Second topic, step and touch potential. Step and touch potentials. Touch potentials. This is very important aspect. We will discuss in details in following templates. So earthing design, calculation methods, selection of material criteria, and requirements in EHV and HV substation earthing design. So measurement of soil resistivity, next topic we will discuss. So resistivity of the soil, where the area has very high soil resistivity. These are the important locations where the earthing designing is very critical. So soil resistivity is not uniform, so we require its measurement. So Venner method is there, 4-point method you can say, and Switchyards method is there. So we will discuss these methods also, how soil resistivity is measured and importance of its measurement. Where soil resistivity is very high, say 1500 to 2000 ohm meter, these areas are become special case. So designing is critical. Earthing designing is critical here. Safe practice. So how safe practice means how safely earthing system is designed. For the personnels and equipments. So here are costly equipments, and personal life is also very important. So we have to protect them safely and design earthing system according to that. So substation earthing, a big question mark you can see here. So what it means, what is earthing? What is earthing? Where it is required? It's required. And why it is required? Why it's required? So these are the three questions we will discuss, and we'll get the more depth in knowledge about the substation earthing. So substation earthing, while discussing, earthing is a very vital part of electrical systems. A well-designed earthing system is necessary to ensure the safety of equipments and the personnel working in the area, and correct operation of the protective devices. So three objectives of the earthing designing is, first one is ensure safety. Second is ensure safety of personnel also, and ensure safety of personnel. Third is safety of equipments. First one, safety of equipments, safety of personnel, and third is correct operation of protective relaying system. Protective relay system. So these are the three objectives of the earthing. So earth, when this protective earthing is required, protective devices, correct operation of the protective devices, earth fault current in the electric system, earth fault current in the electric system, lightning strikes on the equipment and structures. When this earthing system is performing for the safety, in case of the earth fault currents, lightning strikes on the electric equipments and structures, and occurrence of the induced voltages and currents on the equipments, conductors, cables, and structures. So this is induced voltage, means in case of the lightning strike also, lightning strike, induced voltages are there, induced voltages are there. In case of GIS substation, induced currents are present in enclosures, because enclosures are metallic. So earthing becomes very important in this GIS substation case. So switchyard earthing, we will discuss some points. Switchyard earthing means laying of the earth mat and connecting all non-current carrying parts of the equipments of the yard as well as the control room. So in control room, separate earthing is required. Separate earthing, pits earthing system is provided for the control room, and other metallic parts, all the metallic parts in the substation are to be earth, considering equipments and other structures. Structure is there, equipments are there. So these are to be connected to the safe earthing grid, low resistive path or low impedance path. So second point is safe passage of fault current. Safe passage of fault current to enable the to operate protective devices and provide safety to the personnel and equipments. So safe passage of fault current. So earthing grid must not be broken anywhere. Safe for the safe passage. Unbroken earthing grid. Unbroken earthing grid required for the safe passage, or undisturbed path provided, and low resistivity path, low impedance path, low impedance path to be created. Intentional earthing system. Intentional earthing system is created by laying earthing rod of mild steel in the soil of the substation area. So this earthing system is required to improve the or reduce the earth resistance for substation areas. Dangerous potentials, we will discuss now. Dangerous potential, step and touch potential in earthing of the switchyard. So why those are important, we will discuss. So first one is step potential. Step voltage circuit is provided here. Is source, it is the current, RF is the resistance, RB is the body resistance, RB is the body resistance. So this is the complete circuit which is showing. RF is the foot resistance, I think. So potential difference shunted by the human body between the two accessible points. on the ground separated by a distance of 1 pace. 1 pace means between 2 foot, this 1 foot and another foot. So this is a human, you can say, and this is between 2 foot. It is a step potential. It is considered 1 meter length ideally. Here 1 meter ideally, assumed to be 1 meter. So this DF is 1 meter. So this is the path, you can say, and difference is like this. The current will flow like this, and what potential difference will be across the 2 feet. So which will create a potential difference across 2 feet, and that will be a dangerous to the human safety working in the substation. Second is touch potential, the potential difference between the point on the ground and the point on the object. So this is one first point on the, see this is a transformer body, and second point is ground point. So between these two, the current path is created whenever there is a potential difference between these two points, ground point and one point transformer body point where you have touched. So this is a RB is the resistance of the body, and RF resistance of the foot, floor you can say, floor resistance. So this path is created, and human may get electrocuted. So is likely to carry a fault current which can be touched by the person. So very important point. Here also one motor is shown, and motor has got faulty earth fault, and human person if touched to the motor body and his feet on the ground. So this path will be created up to the ground, and this fault current will create a touch potential across these 2 points. After generation of this touch potential, current will start to flow through the body. So dangerous potentials, what are the dangerous potentials in the substation area? We will discuss now. So first one is metal to metal touch voltage. Metal to metal touch voltage. Here human has connected his both hands on the both side of the metal structures. So this is metal structure. Metal structure, metal to metal. Here also it is a metal. So second is step potential between 2 feet. This is also shown here. This is a metal to metal, EMM. Here ES is a step potential. Ideal distance between two is 1 meter. So this remote earth is shown. So remote up, considering remote earth. Third is touch potential. Here is touch potential. So touch voltage is here shown. Whenever a human touches to the transformer body, fault created, earth fault current flows through this up to the ground, and between this his hand touched this point and this point, ground point. So potential across these 2 points is touch potential. Then mesh potential is also shown. Mesh, human has touched this body, his body to the transformer body, and fault path, if earth fault is there, will be like this. So this will be the mesh voltage. Then there is a transferred voltage also. Transfer voltage, you can say, this metallic body, if earth fault is occurred, and here is a structure, suppose structure from equipment metallic structure, earth fault, this current will flow to the structure, and this structure will get structure between this structure and this human touching point to the structure and to the ground point. This will be a transfer voltage, we can say transfer voltage. So equipment is having earth fault, and this current will flow to the metallic structure, and this metallic structure will get in touch with the human body, and human is touching to the metallic structure, and the another feet is touching to the ground. So this will also create a transfer voltage. So these are the different, this is surface potential profile, you can say voltages, how voltages are changing, E transferred or GPR, remote earth is there. So basic shock situations you can see. So these are the potential values, like this it is higher one, these values are shown on the graph. So earthing designing, we will discuss now procedure for the earthing design. Procedure, how earthing is designed, earthing calculations and other all required calculations and other specifications how are done. So to limit the step and touch potential to the working staff in the substation, how, what is the objective of the safe earthing designing? To limit the touch and step potential to the working staff in the substation, provide low impedance path to the fault currents to ensure the prompt and consistent operation of the protective device. So this is also very important point. Third point is stabilize the circuit potentials with respect to ground and limit the overall potential rise. So if there is a fault in one phase, this is very important point. So if there is a on fault on one phase, other two phases experience over voltage. So this over voltage is also dangerous for the electrical power system. So it will create over voltages and stresses on the insulation levels. So there may be a chances of bursting the equipments, damaging the other equipments. So keep the next point, keep the maximum voltage gradient within the safe limit during the ground fault condition inside and around the substation. This is also very important. So voltage gradient is related to the voltage changes with reference to distance. So this distance, as per the distance increases, voltages goes on reducing from the starting point or the fault point, we can say source point. So voltage gradient is also a very important point. So these are the objectives of the safe earthing system design. Very important topic we have discussed. So important parameters. What are the important parameters of the earthing? First one is touch potential. The potential difference between the 2 points, one on the ground where the man may stand, and any other point which can be simultaneously touched by the either hands. So this is a touch potential we have discussed above also. So this is the touch voltage. We have seen. This is the touch voltage. This is the touch voltage we have seen. Okay. So touch voltage we have seen. Step voltage also we have gone through. Potential difference between any 2 points on the ground surface which can be simultaneously touched by the feet. So this is a person and this is 1 meter is the ideal distance, and between 2 feet he will experience the step voltage. Maximum ground mat resistance shall be less than 1 ohm for the substations of 220 kV class and below, and shall be 0.5 ohms in case of 400 kV. So 400 kV we have to maintain 0.5 ohm earth grid resistance. So it is very important and sensitive voltage class. Earthing design what are the input parameters? Input parameters, we can say there is a fault current as an input, duration of the fault current is in kiloampere, a duration of fault current say 1 second or 0.5 second, system voltage is kV as per the given maximum minimum nominal voltage we have to consider nominal voltage. Switchyard area of the grid, we will be designing the grid for that switchyard area, so area is also important. Size of the conductor, we calculate the size of the conductor, and material we have to select. So soil resistivity, it is from Wenner method we have to calculate. Wenner method will give soil resistivity. So distance between the conductors, so this is also very important, distance between the distance or spacing between the conductors, spacing, it will affect the touch and step potentials. So size and mostly the step potential may be mostly affected in the spacing factor. So size and number of vertical electrodes, so this is see, this is a grid we can see, and these are the horizontal conductors, and these are the vertical conductors you can see. So number of vertical and horizontal conductors. So vertical conductors will be required to compensate the fault current. Fault current has to low resistance path to flow to ground. So number of electrodes, vertical electrodes are also very important. So resistance of the crush material layer, so here gravel of 100 mm to 150 mm, 150 mm size is required as a surface layer, which will improve the contact resistance between the uh, human standing on the gravel and the ground. Resistance of the electrode, so resistance of the electrode is calculated as per the IS 3043 and IEEE 80. So these are also important. So earthing designing, output parameters, this we have discussed now input parameters. Now we will discuss the output parameter. We calculate the size of the conductor. Firstly, optimum size. Optimum size is considering the corrosion allowance. Okay. Permissible limit of dangerous potential, step and touch potential. These are also very important. So grid resistance is also, these three factors are the output. Grid resistance we calculate from the formulas. Here length of grid conductor, depth of laying, soil resistivity, conductor resistivity important. So these are the important parameters. The design of earthing system for AC substations requires systematic analysis of various factors and application of proper methodology and criteria for determining design parameters. Second, uses of design parameters for deciding type of earthing conductors, their material and size, very important point, whether GS, GI, MS, copper or other materials, steel. So max, we have to decide this type of material to be selected. Maximum permissible dangerous touch and step potentials, difference of human beings, difference means 50 kg and 70 kg. These are the two weightage of the persons is considered. From this surface layer derating factor is calculated, and other all we will discuss in next part. Just we will discuss the background. Layout of horizontal grid conductor to keep the touch and step potential within permissible limits. So horizontal, this grid, whatever grid we are designing, number of conductors, vertical and horizontal. Grid is to be sufficient to maintain the GPR ground potential lies less than the touch voltage. Tolerable touch voltage. So this is important criteria. Location of the rod, pipe and plate electrodes for control of potential difference and fulfillment of statutory and other requirements. And fourth one, so location of rods, pipes, plate electrodes for control of potential difference. It is also very important one. So where to provide these vertical rods, pipes, plates means earth pits. That is also very important. So fourth, earth electrode for the system, neutral and electronic equipment earthing. So separate earthing is provided for the electronic equipments and also for the neutral and also for the lightning arrestor. Lightning arrestor. This is also very important topic. Size of the earth conductors. The main element of the earthing system of the HVAC high voltage AC substations are horizontally buried main elements, horizontally buried bare strip and round conductors, vertically buried rods, pipe, plate, electrodes. Third one, bare insulated earth lead conductors between above ground earthing points. So these are connecting between equipments and earth grid. The terminals, equipments, structures and underground buried horizontal conductors, vertical electrodes. So this is interconnection and bonding material. And here welding is also provided. Welding is provided for the connections. Exothermic welding is provided. And so interconnections also important. So size of the earth conductors. Main elements we have discussed now for the earthing is the bare strip conductor, round conductors, horizontal and vertical. These are the earth mat materials, you can say earth mat materials. These first two are the earth mat equipments, and these are the risers. So risers are there and connections are there, terminal connections, terminations are there. So this was the very important point, main elements for the earthing mat. So now we will discuss the cross sectional area of the earth conductor, how it is calculated. This some formulas in IS 3043 is S is equal to I root T upon K. K is the material constant. And this is from IEEE 80. So conductor cross sectional area is calculated. This is raised to 0.5 means root of. So I here in this formula I is there is fault current in kiloampere capacity, kiloampere. Here rho is provided, it is the resistivity of the material in micro ohm. Then alpha is provided, alpha is a resistance of temperature coefficient of the material. Then TF is there, TF is duration of the fault current. Then delta is there, density of the material, it is also important. S is the volumetric heat capacity, specific heat of the material, means how much heat material can withstand without melting. So there is a final temperature and initial temperature. Theta 0 is the ambient temperature, theta m is the maximum permissible temperature, final temperature. So these are the parameters required to calculate the area of cross section. So area of cross section is calculated here. Area of cross section is calculated here. So ambient temperature theta 0 and the standard values for the material constant is rho, alpha, delta and S for the type of material. So see, MS is there, GS is there, copper is there. So these are the different materials used. So for these different material, different properties are there. Mechanical strength is there. Mechanical strength you can check. Temperature withstand capacity is there. Temperature withstand capacity. So different materials has different properties. Resistivity is there. So this is the conductor sizing for the earthing. Now second point is corrosion allowance. To standardize the size of the ground conductor, uniform corrosion allowance is 0.12 per year, or the 0.1% per year is considered, considering life of the substation 40 years. So corrosion allowance diameter is 40 years. 0.12 is the percentage loss, and 2 is the both sides of the strip. Both sides of strip. So this is calculated for the strip. Consider 75 by 10 mm strip is there, and this corrosion allowance is on the both side of the strip. So magnitude of the fault current is if 31.5 K, 1 second fault duration, 22 mm is the diameter of the earth conductor calculated, and then after considering the corrosion allowance, it is 32.3 mm. So added 9.6 mm. It is 12%. You can say 12% is added. 12%. So 40 mm MS rod has been selected for the design purpose. So preliminary arrangement now we will discuss of the conductors of the earth electrode system. Here this mat is provided, earth mat, and these are the vertical electrodes. Vertical electrodes, and these are horizontal conductors. Horizontal conductors. Main earthing system is formed of a grid of the conductors, mostly perpendicular to the each other, buried horizontally, usually at the depth of 0.6 to 0.5 to 0.6 below surface of the earth. These may be laid at reasonably uniform spacing. Uniform spacing is to be provided 3 by 3 like this. Cross connection should be provided so as to form the meshes. So meshes has to be formed by the cross connection. The mesh junction should be provided at such points where the multiple paths are useful, such as neutral connections, lightning arrestor connection. Minimum spacing of the conductor is limited by the distance at which trenches can be dug. So typical spacing is 3 meter to 8 meter. However, in non-critical substation areas, 15 meter or even larger spacing can be provided. So spacing between conductors is 3 to 5 meters, and non-critical substations up to 15 meters is the spacing provided. Even larger spacing can be provided. So meshes at this mesh junction should be, so this is very important point. Mesh junction. So mesh junction is to be mesh junction. So smaller meshes are provided like this and are interconnected. So mesh junction should be provided at such point where the multiple paths are useful, such as neutral connection, lightning arrestor, and why this is important. So uninterrupted, or there shall not be any discontinuity, say break up in the break in the continuity path. So continuous path at any condition is to be confirmed. So these meshes are required. Smaller meshes are required in the substation earthing grid. So this was the mesh junction points we discussed. So provision of vertical rods. Now the grid, see, this is the grid, and these are the vertical rods, and this is horizontal. Okay, the grid earth electrode may be assumed to be consist of only horizontal conductors to start with. Vertical rod may be provided at the stage of station where resistivity of soil is likely to vary with the change of season. So driven vertical earth rods of 3 to 5 meters length and with their upper ends connected to mesh junction. So mesh junction is also very important topic, are suitably provided. A vertical rod is very effective if its length is such that it can penetrate to the moist subsoil. So deep well earthing is also nowadays new earthing system provided for the high resistivity soils. So earth mat you can say, see, so this is the earth mat, and vertical rods in blue line, deep driven earth rods. So earth mat in black is shown here. Here dotted red line showing additional conductors, blue line is showing boundary conductor, and this the green line is showing boundary conductor, blue line is deep driven electrodes. So this is the earth mat we have provided. So the main earth mat shall be laid horizontally at the regular spacing in both x and y directions based upon soil resistivity value and substation layout arrangement. So this is also very important one, how the mesh is or the grid is provided. So permissible touch and step potential criteria. The circuit of flow of current through the body. Circuit of flow of current through the body shown in figure shows the IEEE 80. So here, if this is the equipment, and fault current will flow through the body this path, touch and step. This is step and this is touch. So these two different step and touch potentials are shown here. RB is the resistance of the human body, though there is a variation between the hands to hand contact and hand to feet contact, hand to hand and hand to feet contact, hand to hand and hand to feet contact, hand to feet contact. These are the different terminologies. So hand to feet contact, an average value of 1000 ohm has been adopted for the body resistance in IEEE 80. So RB will be 1000 ohms. The calculated step voltage ES, calculated step voltage and touch voltage should be such that the possible body current I is less than the maximum permissible body current. So these currents, body has a some permissible milliamperes below 30 milliampere, I think below 30 milliampere body is safe. The maximum permissible values of the step and touch potential are given for the average body weight of 50 kgs. So 1006 into CSC, this is the surface derating factor, surface layer derating factor. This is the soil resistivity, and this TS is the time of the operation. So these two are the formulas for the step and touch potentials. A 50 to 150 thick layer of gravel crushed rock is usually spread in the ground surface over the earth grid in the substation area to increase the contact resistance between the soil and feet, and thereby the magnitude of the maximum permissible touch and step potentials. So the electrical resistivity of the gravel and crushed rock layer is usually assumed to be 3000 ohm meter. So gravel has 3000 ohm meter resistivity. Attainable value of touch and step voltage should be less than the permissible value. So permissible value is allowable step and touch voltages, and calculated is actual calculated step and mesh voltage. So these shall be less than the permissible value, means allowable. Maximum, so resistance formula, resistance of the grid earth electrode, a simple formula used as follows: Rg is the grid resistance. So rho is the soil resistivity, Lt is the total length of the horizontal grid conductor, and A is the area of grid, H is the depth of the burial of the earth grid. So these three important parameters are required to calculate the grid resistance. Maximum grid resistance shall be less than 1 ohm for the substation of 220 kV class and below, and shall be 0.5 ohm for 400 kV. So 1 ohm is okay for 220 kV and below, and 0.5 ohm for 400 kV and above voltages. So resistance will be reduced as the voltage level is increased. Potential distributions, various mesh sizes. This is very IMP, very important topic we are going to discuss. So here smaller meshes are required. Smaller mesh sizes, various mesh sizes are given here, and what is meaning of that we will discuss. But required is that for higher voltage substations, required is that smaller size meshes are provided, are required, are good, you can say, for the maintaining equipotential bonding. So here single mesh is having 36% of the plant voltage of the system voltage. System voltage is appeared across the grid. So this voltage appearing across the grid is 36% when the single mesh is provided. 100% ground mat of potential, ground mat potential is 100%. This 100% is showing 100% is the of system voltage, or the substation voltage. What is the substation voltage? That is 100% appearing across the ground mat potential, across the mesh. If single mesh is provided, 36% will the voltage across. Now 2 by 2, 2 rows and 2 columns are provided. Here 55% voltage will be appearing across the grid. Say there is a 100 kV, then 36 kV will be appearing here, and here it will be a 55%, means like 55 kV will be appearing across here. Here 70 kV will appear. In case of here 4 by 4 is there, 4 by 4, 4 rows and 4 columns of the smaller meshes, 70% voltage will appear across the ground mat. Here now 3, what is the size of the meshes? 16 mesh, C curve, 16 meshes are provided. 16 means 3, 8 by 8, 8 by 8, 64 meshes. So 64 meshes, D curve. In case of the D curve, this is 16, 4 by 16 meshes. Here 64 meshes in this provided. So this will have the voltage of 80 to 89 maximum percent voltage is appearing across the ground mat. So green single mesh, here curve A is showing single mesh. So this is the 36% voltage is appearing here, 36%. Then B is provided 2 by 2, 60% voltage is appearing. Now see 16 meshes are provided, 80% voltage is appearing. 80% voltage is appearing. Now 64 meshes are provided in D curve, which will be appearing 89 up to 89% of the voltage appearing across ground potential, ground mat potential. So what will be effect if the smaller sizes of the meshes are provided? GPR, ground potential rises, will ground potential will rise will be very less. Means it will be having a equipotential bonding. This is very important topic we are discussing. So this is enough for these various sizes, mesh sizes. It is okay. Then here also 57%, 57%, like 4 by 4 we can see. Special consideration for the earthing design under the difficult condition. So difficult condition for the design of an earthing system are any of all given below. High soil resistivity, limited area in case of laying earth load. In GIS substation it is a restricted or small area. Large magnitude of earth fault current, say 80 kiloamperes and 1 second. These are the difficult conditions for the designing of the earth mat. Soil resistivity may be 1500 ohm meter to 2000 ohm meter. This is also critical area. So difficult conditions for the earthing designing, it is very important one. So multi-layer earthing and satellite earthing. Now we will discuss satellite earthing. This is the main earthing grid. Suppose main earth mat is provided here. Main earth mat is provided here, but the resistance is higher. Then we can provide a satellite earthing connecting. This is a satellite earth grid. If there is a no space available, we can provide at some other space, other location at some distance, some other earthing mat is provided, earth mat. So this earth mat is a satellite earth mat. Earthing system for the 60 kV system. So resistivity is higher. In case of the resistivity is higher and space is less. So 2000 ohm meter is the resistivity and space is less. Space is less. Available space is less. So in this case, satellite earthing is provided. So here 50 by 6 GI earth pit or separation of the 3 meter is provided. 18 meter long vertical ground rods of 32 by 40 mm diameter MS rod, total 42 numbers. Here it is not necessary that your earth rod is electrode is 18 meters. You can have 3 plus meters some at, but kept at the bottom of the borehole, and connected by the strip or pipe to the grid or mesh. So you can have 18-meter depth borehole, and you can put the earth electrode of 3 meters, and this is connected to the mesh through the strip. This, and backfill is there. Chemical backfill is also provided there. So this is the satellite earthing. Earth mat for GIS substation. So here in GIS substation, the grid in the cable cellar is provided. Mesh of size 1 meter by 1 meter. Smaller mesh sizes at corners. Corner 0.5 by 0.5 meter mesh sizes are provided. So in GIS substation, there is a space constraint, and so earth mat or grid is provided at the cable cellar. In that building only you can provide a earth grid, and some other earth mat at the transformer station. Other earth mat at transformer substation outdoor. So the two grids are provided. This is a cable cellar floor. This is a pedestal. So next is metal to metal touch potential in GIS. Very important topic. Metal to metal touch potential. So in case we can touch the two cubicles enclosures, metal enclosure cubicles are touched by both hands. In this case, this is a touch potential across these two. So E touch A minus B potential is provided, and here it is a touch potential across the two different one end is the cubicle and other is the structure on which it is installed. So you can touch like this also. Here also you can experience the touch potential. Second is typical faults in GIS. What are the fault? Internal fault is there in GIS, close external fault is there, and remote external fault. These are the different faults we can see. This is A is the internal fault, B is the external fault, and C is the remote external fault. See, these are the three ABC faults are given. R is the resistance, I is the source current, fault current. This is a return path. Here it is a return path shown. So this is return path to the source. In AC substations, here touch voltage is here and time is here. So touch voltage limit for the metal to metal contact and the typical range enclosure voltages to ground. So E touch and E touch 50 and 70. So 4 seconds is the maximum allowable time. And here voltage is, for 4 second voltage is 60 volt. This is the safe voltage. this safe touch voltage right there, touch voltages in GIS. So 4 second 60 voltage can be experienced for the 4 second or 3.5 second. Here is the breaking point. The way 65 volt, 130 volt, 65 volt, this is the voltages provided for 1.5 second. Here for the 70, here will be 130 volt. This is the 130, 100, 150, 200. So this safe earthing is very important in GIS substation. Earth mat for the GIS substation building. You can see this is the transformer yard. This is a transformer yard. External earthing, external earthing, and this is a GIS area. Here also in cable seller earthing grid is provided, and this outdoor earthing grid, and GIS earthing grid. This is a control room. Control room also has a separate earthing, and lightning protection earthing is also lightning protection earthing grids are separate, but grid is connected to this earthing grid also. So both for combined low resistance path is provided. Earth mat for the GIS substation. So grid, one is grid at the cellar floor and rebar GIS floor also slab. So this above ground GIS enclosure, and these are connected to the floor slab rebars at the GIS, and GIS grid at the cellar floor. So these are the interconnections shown. And vertical 6 meter long road, main grid at the yard. These two grids are provided, cellar and here also, and the floor strips are laid along the floor also for the interconnections of the earthing. And these are the vertical 6 meter long vertical rods, earthing rods, earth electrodes. So earth mat is earthing mat for the GIS substation is provided in this way. So earth mat for the GIS substation. AIS grid 600 below FGL, and floor slab GIS room 2 meters above FGL. Here GIS grid at 2.5 meters below the FGL, covered with the 50 thick concrete is provided. Above ground GIS enclosures. These are the enclosures are connected to the floor slab GIS room at 2.2 meters above FGL. So here is a FGL, and here 2 meters is the distance. Grid is at 2.5 meters. Here it is this grid is 2.5 meters below. So soil resistivity, so this was the GIS earthing we have seen. Soil resistivity measurement and analysis. This is also a topic we have already discussed in our first part, but we will discuss in shortly. Soil resistivity of an area is not constant, but varies with the weather condition as well as the type and the nature of the soil. It is also it can also vary with the depth below the earth surface. So depth is also very important. Weather conditions also important. Type of nature of the soil also important. So soil resistivity will be dependent on weather condition, nature of soil, and depth of earth surface, depth below earth surface. Soil resistivity measurement may be preferably made during the year when the soil is dry. So in summer vacations, summer it is done, and temperature is low. Temperature is also low. So in mostly cold season, cold season. we can consider the measurement of the earth soil resistivity. So here is a Wenner 4-point method. Earth tester gives directly the ratio of potential difference between the earth electrodes P1 and P2 and current I as the resistance R. Connection of the 4-point electrodes is shown here. So here instrument, measuring instrument is provided. Here potential terminals and current terminals are provided. Potential terminals are internal. These two are potential. P1, P2, and these are current terminals C1, C2. Spacing is provided, yes, same spacing between the same spacing between electrodes. So soil resistivity formula here. 4 probes are driven into the earth along the straight line at the equal distances s apart, driven to the depth E. The voltage between the two inner electrodes is then measured and divided by the current between the two outer current electrodes to give the value of the soil resistivity as per the following equation. So soil resistivity is given by this formula, where rho is the resistivity of the soil in ohm meter, R is the measured resistance, S is the spacing between the adjacent electrodes, E is the depth of burial, V is the voltage difference between the two inner electrodes, I is the current flowing through the outer electrodes, C1, C2 is current electrodes, P1, P2 is the potential electrodes. So safe practice. We'll discuss now safe practice of the earthing. So safe practice is we have started implementing maintenance free earthing, treated earth feeds like marconite chemicals are provided as a backfill. So normal soil, cast iron cover inch. This is the earth feed details we have provided. 3 meters earth feeds. So here 3-meter earth feed is provided. The 3-meter earth feed. Copper GI electrode of up to 40 mm or 20 mm, 70 to 17.2 mm 3 meter is also provided copper, and GI pipe is 40 mm 3 meters. Ground enhancing material, backfill, ground compound, charcoal and salt. These are the conventional components, fill components. Brick wall is there. Here this chamber, earthing chamber is provided. Here connection to the 75 by 10 mm GI strip, 3 numbers 110, 12 by 25 volts, 4 nuts. These are the details provided, and the IS 304 also it is provided. In rocky soil, some different provisions are done. Say 6-meter depth is provided, and 3-meter earth electrode is provided. So difference is only this depth of the burial, depth of the borehole. Borehole is 6 meters. This is the change. Other pipes specification will change as per the requirement. 17 mm 3 meter, 80 mm 3 meter, 80 mm 40 mm 3 meter, copper and GI pipes, copper and GI pipe electrodes. So different pipes and different electrodes will change the different. Black cotton soil is there, 300 by 6 meter borehole. Existing rocky soil also around. Here exothermic weld is the important point. Exothermic welding, which is required to make a one metal, like joint is not there, these will be combined or the welded together to become one, and zero resistance between these two. So this is also very important point, exothermic welding. So safe practice, sheet wires are strung to provide DLSLP for the yard equipment, hence do not ignore to provide earth wires if removed. This will be having current division. Benefit in the earthing. Benefit in earthing. Safe practice. Always use clip-on meter, digital meter to measure the healthiness and earthing pits of earthing pits and equipment structure earthing. Never open the earth connections. This is very important. Whenever there is a live substation, never open earthing conductor, earthing connection. Very important. Safe practice. Never keep risers unconnected to the earth mat. Never open the connections in live switchyard. Grass, plants, shrubs shall be removed from the yard. Very important. Safe practice. Laying of the earth mat, proper welding as per the standard earthing philosophy is to be provided. So, existing earth mat, new earth mat being welded, flexible copper connections between the auxiliary earth mat and the existing earth mat. So these weldings, exothermic welding or whichever we have confirmed during the detailing shall be provided. So this was the safe practice for the earthing installation maintenance. So I hope you understood good and you get help to improve your knowledge through this video, this lecture. We will be discussing another part, third part, calculations as per the IEEE 80 and other criterias. Thank you.